Thanks for the introduction, Colm. So, like Colm said, I'm an electrochemist and I focus on liquid-liquid electrochemistry. So that's quite a niche area of electrochemistry, so I'll explain some of the fundamentals. And I use it for many different applications, but I'll just describe two today. So how to make a biomedical device using this theory, and also work towards solar cells, or you could put it another way, artificial photosynthesis. So Colm's given my background nicely there, and I call it the circle of academic life. So I started here, and to prove it, there I am. It's the 2005 chemistry class. And then I went to Tyndall, and then to Limerick, and recently in Switzerland. So EPFL is a very nice place to work. The guy who basically invented my field, he's still going, and he's working here at EPFL. And it's quite a nice place to work because it's Switzerland, they have lots of money and they like spending it on science and libraries. So this is their library here, and it's Switzerland, and they designed it to look like a piece of Swiss cheese. Seriously. And the circle of life is complete. I'm back here now and working towards my own independent research, get my own ideas and really seeing where I can go with them with a group maybe. So I'm going to talk about biomimetic chemistry. So biomimetic means inspired by nature. And I work at liquid-liquid, or as I call them for a lot of the talk, soft interfaces. So this is a phospholipid monolayer, and it's a membrane in cells, and it separates an intracellular space from an extracellular space. So this is water, and this is water, and the phospholipid membrane is a very hydrophobic entity. So this is the oil phase. So this means there's two soft interfaces, one here between the water and the oil, and one here between water and oil. And if you can understand what's happening at these soft interfaces, you can really mimic nature. And nature uses these membranes in normal photosynthesis. So if you can understand how nature does photosynthesis, maybe you can make an artificial variant of it. And also these are proteins here, and they're capable of very selectively transferring ions from the outside to the inside, or vice versa in the cell. So we, in some of my very early research, and something I'm going to pick up again, we mimicked these proteins in the membrane to create ion-sensitive sensors. So we want to detect ions, and ions are everywhere. They're in your body, and also they're in the environment, and some of them are very toxic. So this is the Z scheme here of artificial photosynthesis, and plants, plants have no semiconductors in them. They absorb light using dyes, so basically molecular species. And then there's a relay here, so they have molecular relay to achieve charge separation. So when you absorb light, you might get an oxidized and a reduced species, but it's only useful if you can keep them away from each other. You want to prevent recombination. So the ultimate source of electrons is water, and eventually those electrons will be used to reduce NADP cation to NADP. So this is kind of like the fuel in the body. So this is the kind of research I want to mimic. So this is a scary looking diagram, but I'll go through it very easily. So it's this is a liquid-liquid interface. So here we have water and here oil, and where they meet, they form an interface. But the interface is a really tiny area. It's only 1 nanometer in thickness. And when the aqueous and the organic phase meet, it's called the mixed solvent region. You'll have some ions or some electrolyte solvent from the water, some electrolyte solvent from the oil, and it's all present here in this 1 nanometer thick region. So from an electrochemistry point of view, it's a bit unusual, because in a normal electrochemical setup, you'll put a piece of metal, basically like platinum or gold electrode, into an aqueous phase. And there's something called a double layer created at the surface of that electrode. But here I actually have two double layers in my electrochemical setup, one on the aqueous side and one on the organic side. And we call it two back-to-back diffuse double layers. And what I want to do in my experiments is I want to apply a potential across the interface. So it's like applying an electric field between the water and the oil phase. And in effect, what I'm doing is I'm making the aqueous phase more positive relative to the oil phase. So that means if there's something positive in the aqueous phase, like a cation, it'll want to get out of there as I make the aqueous phase more positive relative to the oil phase, and it'll transfer from water into oil. And when that happens, I can see that signal using my electrochemical equipment in the lab. So this means that I actually use the liquid-liquid interface as a working electrode. So a definition of a working electrode will be the interface or the electrode at which the process of interest that you want to detect takes place. And in my case, that is the liquid-liquid interface. That's where the interesting thing in my experiment is going to happen. So practically, how do I do that? How can I polarize the liquid-liquid interface? How can I make that aqueous phase more positive relative to that oil phase? Or the opposite, I can make the aqueous phase more negative relative to that oil phase. So there's a very important equation in electrochemistry called the Nernst Equation, and a form of it exists that can be applied to liquid-liquid interfaces. So with normal electrochemistry, we're always thinking about electrons moving and coming and going, so reduction and oxidation. That's not what I'm talking about here. I'm talking about the movement of ions. So there's no electrons involved in my in this form of the Nernst equation. So this here is the potential difference between the water and the oil phase, called the Galvani interfacial potential difference, give it its proper title. And this here is a constant. And this constant is, in effect, the amount of energy it takes for an ion in solution to move from the water into the oil phase. So each ion will have its own charge, and it'll have its own way in which it interacts with its environment. So each ion will have its own unique standard ion transfer potential. And this is important for sensor applications because every ion will transfer at a slightly different potential, and that gives selectivity to our sensors. If we know where that ion transfers and we detect a peak at that potential, then we can say, okay, that's sodium, that's potassium. So these are your normal constants, your gas constant, temperature. This is the charge in the ion you're looking at. That's Faraday's constant. And here, you don't have the ratio of the oxidized and reduced species. You have the ratio of the concentration of the ions in the water and the oil phase. So if you look carefully at this equation, there's two ways in which we can manipulate it. We can manipulate it externally. So this is my experiment here, where I manipulate it using a potentiostat. And when I do that, I change this term here. I change the potential difference between the water and the oil phase. And when I do that, all of these guys here are constants. Nothing's going to happen to them. The only thing that can change in response to me changing the potential difference across the interface is that I'll change the ratio of the ions in the water and the oil. And when this ratio changes, what that really means is that a positively charged species or a negatively charged species, an ion, is moving from oil into water or vice versa. So that's externally changing the ratio. So I do that using this setup. So it's called a 4-electrode electrochemical cell. The oil phase is usually on the bottom just because it's more dense. It's chlorinated solvent I use, or a fluorinated one, so it's more dense than water. It'll naturally go to the bottom. And I have 4 electrodes, 2 reference, 1 in each phase, and 2 counter electrodes, 1 in each phase. The reference monitors the potential, the counter brings the current into the system, and my working electrode, in effect, is the liquid-liquid interface itself. So, okay, using this setup, I can apply a potential difference across the interface, and I change the ratio of ions, and you get this kind of thing here. It's a cyclic voltammogram. So this is basically the current versus the potential, and you get this shape. So the length of it is called the potential window, and it's limited by the transfer of the aqueous background electrolyte ions. And they're usually lithium chloride. So when lithium transfers at positive potentials, so here I'm making the aqueous phase more positive than the oil phase. So anything that's really, really positive in the aqueous phase will want to get out. And here it's lithium, and here it's the opposite. I'm making the aqueous phase more negative than the oil phase, and this time chloride will want to escape out of Cl-, will want to escape out of the aqueous phase. And in between these two limits, I can detect any ion of interest. And if I'm lucky enough that the ion I'm looking for has an ion transfer potential, so this term, if it appears in between these two limits, then I can detect it. I can make a sensor to detect that ion. Now, very importantly, and especially for any organic chemistry people in the crowd, you can change the ion transfer potential at a liquid-liquid interface chemically by distribution, by controlling this term. So this is the concentration of the ion on either side of the interface. And dependent on the ion you pick, you can make the interface positively charged, positively polarized, or negatively polarized. So this guy here is a TB-, we call it, very hydrophobic molecule, but it'll partition between the aqueous and organic phase. You might have like 10,000 of them in the oil phase and 1 of them in the aqueous phase. And then that'll set up a ratio here, and that ratio will set the potential positively. I can polarize the interface negatively using this guy as the common ion. So why is that important for organic chemists? So everybody knows organic chemists love doing extractions. So they make their compounds, they shake it up, and they extract the impurities maybe into the oil phase and they throw it away, and they're left with their purified compound in the aqueous phase, or vice versa, whatever they want. So just say I get a liquid-liquid interface like this, and I do my cyclic voltammogram using my 4-electrode cell. I'll see something like this. I'll get this voltammogram. And this peak here stands for the movement of a cation from water into oil, and the opposite is on the reverse. It's the movement of the cation back from the oil and into the water. So this here, this red line, is its standard ion transfer potential. That is the amount of energy basically it takes for that cation to move from water into oil and back again. So I know now that if I polarize my interface positively, it's going to be in the oil phase, and if I polarize it negatively, it's going to be in the water phase. And I can do that by adding these molecules to the both phases. If they're both in both phases, so if I have this guy in both phases, I'll extract my cation in 100% efficiency nearly to the oil phase, and if I have this guy as a common ion, I'll extract everything to all of this cation to the water phase. So I don't think that when the organic chemistry gang here are looking at their extractions, they're also thinking about the Nernst equation, and that's where I want to come in. I want to bring a bit of physical chemistry to the organic chemistry department. Opposite happens with an anion. Instead of, so here you're making the aqueous phase very, very positively charged. So this means that the anion is loving that, and it's going to stay in the aqueous phase. And when you make the organic, when you polarize the interface negatively, the anion is going to want to get out of there, and it's going to want to go into the oil phase. So this is useful, and we can, maybe more interesting situation is when you have two cations and you want to separate them. So I have two cations now, so this is theoretical. So this is my CV, and I get a peak for cation 1 here at kind of negative potentials, and I get a peak for cation 2 here at more positive potentials. So basically, cation 1 will, if I apply potential here, cation 1 will be in the oil phase, but cation 2 is more hydrophilic. So I have to apply a much more positive potential to force it from the water phase into the oil phase. So actually cation 2, it takes a lot of energy to move it into the oil phase. So if you look here between the green and the red lines, you have a region where cation 1 is in the oil phase, but cation 2 is in the aqueous phase. And if I polarize my interface using this common ion, so this is very simple molecule, tetramethylammonium cation. So if I have like tetramethylammonium chloride in the aqueous phase and tetramethylammonium perchlorate in the oil phase, I'll polarize my interface here, and I will keep cation 1 in the oil phase and cation 2 in the aqueous phase. So I've managed to separate two cations now just by knowing where knowing the amount of energy it takes to push them from water into oil, and then polarizing the interface using the right common ion. So this can be applied then to flowing conditions. So a lot of like processes in organic chemistry involve flowing conditions for purification. So the top here is my aqueous phase, and this time I'm polarizing my interface using these electrodes, and this here is my oil phase. So in comes my mixture of cations and anions, and I polarize my interface at negative potentials, and the cations are forced out, and I only have my anions leaving in a pure form. So now I do the opposite. So this time I'm polarizing my interface positively, or polarizing it positively, and I'm polarizing it negatively, and I'm forcing the anions out, and in comes a mixture of anions. And if I apply the right potential at the interface, I can separate the two anions, because it's going to take, even though they're both anions, they'll have different structures, different charges overall, and it'll take a different amount of energy to move them from water into oil. So I can purify an aqueous solution by flowing it over an oil solution and applying the right potential. So this is powerful, and I think it'll become more common, and I think eventually this is definitely a use of liquid-liquid electrochemistry that will make it to industry. So also, a lot of people do phase transfer catalysis. So what that means is that basically a molecule in water will have a different reactivity when it's in oil. So the same molecule, its reactivity is dependent on the solvent that it's dissolved in. And one experiment that I spent a lot of time working on was the hydrogen evolution reaction. So a proton basically is reduced to hydrogen gas, and it's reduced by a reductant. But so this is the electrochemical potential of the proton in water at 0 volts, and it's different in oil. It's 0.55 volts versus the standard hydrogen electrode, so on the same scale. And this means basically that it's much easier to reduce in a proton in oil is easier to reduce than a proton in water. So it's probably less hydrogen bonded, it's easier to turn it into a gas. Protons are very hydrophilic. You can see that it takes a lot of energy to move it from the water phase into the oil phase. You really have to polarize the interface very, very positively. That aqueous phase needs to be very positive to push that proton across. But if we use Tb minus, we can do it, and that's what I did. I put Tb minus, so lithium Tb in the water phase, and a very hydrophobic version of it in the oil phase, and that pumped my proton from oil into water. And then this green thing here is decamethylferrocene. It's a reductant. It just reduces a proton into hydrogen gas, but it can only reduce a proton in oil. It doesn't have enough reducing power to reduce the same proton in water. And magically, this is a spontaneous thing, you start getting hydrogen evolved at the liquid-liquid interface, and the bubble is growing, and really what's happening, it's a bulk reaction, and the hydrogen is migrating then to the interface, and the bubble is growing, and that'll keep growing and growing and growing, and eventually it'll pop up, and you get hydrogen evolved. So that's all nice. So what I wanted to do was catalyze the reaction, and what I did was I just basically, we call them floating catalytic wraps, but basically it's just a catalyst, and I sprinkle it on the interface, and that changes the kinetics of the hydrogen evolution reaction. So any catalyst that catalyzes the hydrogen evolution reaction on a solid electrode, it also did it at the liquid-liquid interface. And I did a lot of papers then studying the different kinetics with the different catalysts that we looked at. So now back to the sensor work. So I want to make biomimetic sensors. And the principle will be an electrochemical signal generated by charge transfer, that's an important word there, charge, from across the water-oil interface by polarizing the interface, so using a potentiostat externally. So the charge transfer I'm looking at is ion transfer, not electron transfer, and also assisted ion transfer. So sometimes the molecule is too hydrophilic. You can't apply enough, you can't make the aqueous phase positive enough to get it to move across. And in that case, you use something called an ionophore. And basically the ionophore goes to the interface and it grabs the hydrophilic species, and the ionophore is usually hydrophobic, and it shields some of the charge of that species in the aqueous phase, and it brings it across at a lower energy. So we can then look at that. So this, I'll talk about this later. This is a photo-induced electron transfer at the liquid-liquid interface, and that will be the basis of the artificial photosynthetic work. So my strategy for making a new biomedical device will be, I want to use ionophores. So ionophores can be very, very selective. They can be a mixture of cations in solution, but the ionophore will only pick out the one cation that you're interested in. I want to miniaturize my sensor. Miniaturization has a lot of benefits besides making it small. You can actually improve the sensitivity of your sensor. So sensitivity is basically, you get a bigger change in current or bigger change in signal for the same change in the concentration that you're looking at. I want to move away from pure oil phases. I want to create some super hydrophobic ionic liquids. So these have two big advantages. They're non-volatile, so they're more easy to make a sensor out of, and also they're less toxic. So again, good for sensor development. And this will lead towards a new class of biomedical devices. So this is the very, very first paper I ever did when I first went down to Tyndall, and an Italian group made ionophore for us. And this is basically assisted ion transfer. And I think it's an ideal opportunity for proper interdisciplinary work here between organic chemists and organic chemists here in UCC. So if I can get some organic chemists to make me ionophores, I put them into oil phase, and they're going to go to the interface, they'll pick up that ion, and they'll move it in, and bang, we got a sensor. The hard part is making the ionophore. I get the easy bit. So what we did here is this ionophore can selectively discriminate between chromium-6 and chromium-3. So it doesn't sound like a big deal, but it is, because chromium-6 is very, very toxic. And we want to detect this guy. And I'm not only detecting it, I'm actually removing it from the aqueous phase. So I'm also cleaning that aqueous phase. So it's about a detection system, and if you scale it up, it will be a system of wastewater purification. And you get a signal like this. So this is the transfer of, this time it's a negatively charged species. So it's a transfer here from oil to water, and then from water back to oil. And you don't see it. You see here is at the very end of my potential window, because it's very hydrophilic. So you only see it because this guy here shields some of that big charge, and it allows it to move across the interface at a lower energy that we need to apply using the potentiostat. So that's a real practical application of liquid-liquid electrochemistry. A lot of my PhD was focusing on miniaturizing the sensor, and Blow and Tyndall, they have a fantastic fabrication unit, the central fabrication facility, and they have a technique called E-beam lithography. So these are SEM images, so using a very powerful microscope. And each of these pores is tiny. Like the biggest one here is 250 nanometers, and we made arrays. So what we're doing here is, when you miniaturize, we're basically putting this chip here at the end of a tube. We put the water phase in here, and the oil phase will go into the tube, and when we dip it in, we got a liquid-liquid interface. But the area of the interface is defined by these pores. So we polarized our interface, and we did a lot of fundamental studies on this. So there's a lot of different things happen when you miniaturize the interface, and the big one is you increase the current density. So not current, so your current will be smaller actually, but you increase the current density. So that's the current per area. And that's because you're going to get a change from a thing called linear diffusion at big electrodes, which is not very efficient, to spherical diffusion at micro electrodes. And the way I like to think of that is that the ion is like attacking from all sides, and it's a bit more efficient way of, it's better mass transport. So it's a better way of making a sensor. And our sensitivity increased when we go from the big interface to the middle one, micro version, to the nano. So the micro one is my favorite, because it gives you good sensitivity, but it's way easier to do the experiments, because if you're making a nanopore, you got to make it in a nano-thin membrane. So the technique is basically a laser beam firing at silicon nitride, but it's removing the atoms of the silicon nitride, and it's a laser beam, so it's expensive. And also, eventually, if you're making a tiny pore, eventually it'll fill in. So you have to make it really, really thin. And so the actual thickness of the membrane I was using was 100 nanometers. So if you look at it, it breaks. So I much prefer using the micro interfaces, and we've got a lot of experience with this, and we kind of use this. This will be what I'll really use to make a sensor of it. It's robust, but it gives good sensitivity. This guy is very nice for fundamental studies, and that's what I'll use those for in the future. So this is just another example of some experiments I did. So here we had a mixture of oligopeptides, and we used this ionophore, very boring one, dibenzo-18 cron 6. And here I just want to show that different species transfer at different applied potentials, and that means that we can detect two things in a mixture, and we get a nice signal. And I just want to show as well that background subtraction is good for improving the clarity of your signal. So here is the actual raw data, and this is when we basically subtract that black one there from all the rest of them, and we get a nice clear signal. So just background subtraction can be a nice thing to use to think about when you're making sensors. So this is the future. So I'm going to do a collaboration hopefully with Dr. Jared McLaughlin, and we're going to start out making this ionophore. So it's a huge, massive, bulky, hydrophobic ionophore, and we want to use it to create an ionic liquid. An ionic liquid basically is a salt, but the salt is molten, it's moving around the place. So it's actually a solvent. And we're going to use this as our oil phase. But at the moment, this guy, even when we do make it, I know that it's not the best, because it's going to be too viscous, and the diffusion coefficients will be very, very small. So that means that my current will be very, very small. So I'm not going to get great sensors out of this unless I heat it up to 80 to 70 degrees, which I don't really want to do. So the goal of the project will be to make new anions where we make it kind of unsymmetrical. So we'll take off two of these guys and replace it with maybe alkyl chains, and then it'll pack be more difficult for that kind of species to pack together, and that means it'll be should have in theory a lower viscosity, and it'll be much more easy to use in a real sensor. So that's a big goal of ours. Another maybe dream at the moment is to replace this cation with a cation that is also an ionophore. So that means that the cation will be selective to certain ions in solution. So it'll be a task-specific, super hydrophobic ionic liquid, and that'll be a really good sensor. Like, it'll be non-volatile, it'll be sensitive, it'll be capable of detecting species like selectively. So it's got everything going for it, and it also operates on a different principle to normal sensors. All normal sensors with electrochemistry look at electrons coming and going, and those are limited by things like, okay, this molecule doesn't get reduced, it doesn't get oxidized, so I can't detect it. But if you detect the entire ion, just push it across the interface, then I can detect that molecule, whereas normally I wouldn't be able to electrochem it. So that's my sensor application. So the last part is trying to make a solar cell. So this is what we're looking at right now. So we have our water and our oil phase, and in between the two, we're creating a photoactive interfacial film. So at the moment, we're not really making a solar cell. We're just looking at charge separation at the liquid-liquid interface. So I have a donor species, and it gets oxidized, and an acceptor species, and it gets reduced. And that only happens when I shine light on the film. And I'll explain why in a second. But the real trick of this is that this guy's hydrophilic, this guy's hydrophobic. So there's an inbuilt reason for these guys not to interact with each other. And if we do this properly, we will minimize recombination because the differences in the solubilities of the two species. So this anion doesn't really want to be near the oil phase, and this cation doesn't really want to be near the water phase. So they get away from each other, and we minimize recombination. And now that gives us a chance to maybe store some of that solar energy. To really make a solar cell, we need to complete the circuit. We need to get this acceptor interacting with the electrode and releasing its electrons, and then coming around here to close the cycle. So that part I'm not working on yet. So baby steps, we'll try and understand first charge separation at the liquid-liquid interface with some maybe novel acceptors, novel donor species, and making the film. So here is our liquid-liquid interface again, really tiny area, 1 nanometer. We have our dye, so making the film at the interface. We shine light in it and it gets excited. And then it pops an electron into this acceptor species, which gets reduced. And then the ground state is regenerated by a donor species popping an electron in there. So we have our aqueous acceptor and our oxidized donor, and our synthesizer has been reduced. And this guy can't be reduced by this donor. Only in the presence of light can we get this oxidation reaction occurring, or reduction reaction occurring. And the difference between the redox potential of this guy and this guy will be basically the amount of solar energy that you've stored in a perfect world. So we've actually had quite a lot of early success. So I have a very good PhD student at the moment. He's up in the crowd there, and he's been working on making films of porphyrin at soft interfaces. And he's managed to do it. So here, this purple solution is the porphyrin, the dye, and this yellow film here at the liquid-liquid interface is a film of porphyrin that has been electroadsorbed at the interface. So a lot of the work here was like getting the right pH conditions, looking at the different pKa's of this carboxylic functionalized porphyrin, and also changing the electrolyte. So there's a few tricks to this. But the incredible part about this film is that when we take out all of this aqueous phase and we replace it with a buffer, the film is there. It is completely stable. It's super robust. It's self-healing. So actually I think this is a major breakthrough. And it's the first ever film of this kind I've ever seen at a liquid-liquid interface. And we electrochemically can characterize how much of this porphyrin is on the interface. So we just do a CV and you get a peak above, like you get 2 peaks, and you can, if you measure the charge under these peaks, you can determine how much of the porphyrin is at the interface. And all of it is still there after we go quite mechanically disturbing the system, taking out the aqueous phase and putting it back in. So this guy is proper robust. Is it photoactive? Well, here's your proof. So this is the CV. So the black one is when we don't shine light. This here is the absorption and desorption behavior of the film itself. But in this region here, we're turning our LED on and off, on and off, on and off. And yeah, this is photocurrent. You see the current increase when the light's on, and it disappears when the light's turned off. And we're changing the potential here. And what changing the potential in reality does is it's changing the rates of recombination, rates of electron transfer, rates of photoproduct separation. It's kind of changing the kinetics of the reaction. So it's not so clear in these, but in more experiments that we'll do in time, you'll see a big difference between the shape of these photocurrents depending on the applied potential. And that'll tell you a lot about what's called like the dynamics of the system. So this here, in this particular experiment, I have decamethylferrocene, so a ferrocene derivative as my donor, hydrophobic species in the oil phase. And I just have oxygen, just oxygen in the air is my electron acceptor, we believe. We still have to do a few controlled experiments on that. We'll just do it under deoxygenated conditions, and I'm hoping this photocurrent will go way down. So opposite, you can do the opposite. You can, so we're going to do a collaboration with some people in the organic chemistry department to make quinones, and they'll be acceptor species that will be in the oil phase. and we'll pick up and the donor species might be iron 2 plus species in the aqueous phase. There's a lot of things you can play with here. So photosynthesis, natural photosynthesis, uses a thing called plastoquinone. So yeah, I think we're on the right track here to really have a biomimetic system. So can I class this as frontier research? Is this a big deal? Yeah, I think it is. So the photocurrents are directly proportional to the interfacial surface concentration of the porphyrin. So any porphyrin that's floating around in the aqueous phase, it might as well not be there. It's only the porphyrin that's at the interface in that 1 nanometer region that's active. So that means that if you make a film, you really pack in the porphyrin into that small 1 nanometer thick region, and you're going to get the biggest photocurrents you can imagine. We get what's called significant incident photon to current efficiencies. But I don't use any solid electrodes. Everything here is happening at a liquid-liquid interface. All complications with solid electrodes are gone. So this is a new concept. I don't care about charge traps at the surface of TiO2. I don't have TiO2. So this is new. This is different. This is weird, you could say. But it's working. There's huge potential for scaling. Again, I don't have any expensive semiconductors. I just have a big vat of water, a big vat of oil. I put a bit of electricity into it. I make my film. And if I can work out, like if we go back to this, if I can close that circuit, yeah, we'd have a big, huge vat on the roof with super toxic chemicals that will, yeah, it'll do something. It'll be a solar cell. And it's self-healing, so people love hearing that. So if you stick a needle into the interface and you take it out, the hole will close. Future directions. I want to make more films, so this could be tricky. With different porphyrins, maybe chlorophylls, phthalocyanines, there's a lot of different kind of light active molecules out there to play with. I want to collaborate with people. I want to collaborate with the organic chemistry department to make new donor and acceptor species. So these will be designer molecules. We need the right redox potential, we need the right solubility, things like that. I want to photochemically characterize the films, so that's directly the next thing we'll do. There's a technique here called IMPS. So it's a horrible name, intensity modulated photoelectron spectroscopy. Basically, it looks at charge transfer dynamics, rates of recombination, electron transfer, stuff like that. So we want to. This was basically invented for dye-synthesized solar cell types, normal solar cells. But we have our setup. Our liquid-liquid interface can be interrogated in the same way. I want to collaborate with molecular dynamics simulation experts. So we have this up and running with a guy called David Chung in Galway. Luckily, like the day I started here, he started in Galway. And he models just things that happen at liquid-liquid interfaces. So he's going to tell me why under my very, very specific experimental conditions that film is formed. Whereas in other experimental conditions that are almost identical, you don't form a film. You just kind of have some absorbed monomers. I want to develop, this is the big and the hard part, I want to develop a suite of spectroelectrochemical techniques. I want to look at that film with UV vis, I want to look at it with Raman, and I want to look at it with fluorescence. But to do that, I need to have a thing called total internal reflection. I want to have the light source coming in and hitting the interface and then coming out to the detector. That's not going to be tricky, so they're not going to be easy. So I'm going to get some help from here. Colin Dwyer is going to help me with UV vis, and he'll help me with the Raman, I hope, as well. And then I also have a French collaborator in Nancy. So my student Andres is going to go to France in November. He got a Ulysses grant from the IRC to study Raman. And also, there's a Japanese group that has taken an interest, and they'd like to look at our films with fluorescence. So we'll have some help there. So that's the end of my solar work. I'm not going to talk about this. This is just a quick snapshot of other things I do, or plan to do. So all I've been talking about has been photosynthesizer molecules. They have many other applications besides solar energy. They're used in photodynamic therapy. So this is a cancer treatment. And basically the dye absorbs the cell membrane. It can be taken in by the cell, and tumor cells take in more dye than healthy cells. And if you shine light on your area where the cancer is, the photosynthesizer creates a thing called singlet oxygen, and it destroys that cancer cell. But in theory, your healthy cells should be fine. But I want to modify the liquid-liquid interface with phospholipid monolayers. So Stephen's going to be doing that starting in a couple of weeks. And we're going to absorb dyes and see can we improve it's called structure-activity relationship of dyes on biomimetic interfaces. I spent a lot of time in the last couple of years looking at what I call plasmonic soft interfaces. So I made films of gold nanoparticles at the liquid-liquid interface, And gold is nice material. It does a lot of different things. So if you have no gold in the interface, like was true, if you have gold, it could act as a mirror, so it's an electrovariable on-off mirror. That's tricky. It's easy to get the gold on, pretty much impossible to get it to come off. And a recent thing I did was we catalyzed the oxygen reduction reaction in alkaline conditions on gold at the liquid-liquid interface. So this is another direction that eventually, if I get funding, I'll go off and chase a lot. So that's it. Just like to acknowledge my student, PhD student Andres, doing some fantastic work, as you can see, with the porphyrins. Dr. Colin Dwyer, my mentor, and the funding agencies. So thank you very much.